Hello there. Today we'll look at LLaMA Pro, Progressive LLaMA with block expansion. This paper takes a LLaMA large language model, specifically a LLaMA 7B, and adds some layers to it. Now, they do two things in that way. First, they add layers in order to teach it new stuff. And second, they don't want it to forget all the stuff it already learned. So this is a method that is going to allow for some sort of continual learning, but avoid the catastrophic forgetting problem that's associated with it. What you're going to get out of this is a model that is kind of picks up the stuff that you want to add to it in terms of knowledge. So in this particular case, you can see that the LLaMA they originate from, now this is LLaMA chat, but so the comparison here is a bit weird, but this is LLaMA chat and they compare it to their instruct. But what actually happens is there is the LLaMA 2 base model 7B. They take that, they expand it to their LLaMA Pro, and then this one gets like instruction tuned to become the chat model. Actually, there is even a LLaMA 2 instruct, right? And then this one also gets instruction tuned to become the instruct model. But in any way, they compare the two resulting models right here, one being just a regular process and one being the result of this block expansion route, adding in new data. So once you do that, the original LLaMA, as you can see, is pretty good in these tasks down here, but then falls short on kind of these tasks. Now, what are these tasks? These tasks are things like coding. These tasks are math benchmarks and so on. And if you, for example, take a coding model, sure, you can take CodeLLaMA, and that's pretty good at coding, as you can see right here, but it falls short in kind of this domain right here, where it's the language understanding benchmarks, abstract reasoning, and so on. So the general wisdom being the code, or the data you put into these models will be reflected in the things they can eventually do, which is quite natural. So what they say is, hey, look at this. We can now take a data set that contains code and math specifically. Their data set contains code and math. And we can take the red one and we can push that out. We can push the red one out to become also good at these tasks. And that would be the resulting yellow right here. And as you can see, it is still good on the other tasks. Now, something leads me to believe that they have chosen the tasks they list on this wheel pretty carefully, so that their thing would make like a nice circle, or they've just normalized the axis to be so. That's probably it. But you can see that wherever the original LLaMA was lacking, they can kind of add that by adding data with this new block expansion and training and fine-tuning method without forgetting the capabilities that the model has on the old tasks. And that's the whole gist of it. How do they do that? As I said, they add layers, they freeze everything else, and then they fine-tune the layers they added. And we'll look at exactly how they do that. So they say, the humans generally acquire new skills without compromising the old. I don't think that's necessarily true. So if you have, I don't know, you get into it pretty quickly again. Let's say you played an instrument when you were younger, and then you didn't play it for a whole lot of time. You kind of have to get into it, right? Like you don't know the songs anymore. Your finger memory isn't as good but point taken. It happens a lot more to machine learning models to forget stuff. So they say they propose a new post-pretraining method for LLMs. What is post-pretraining? So you generally have pre-training, which gives you the original large language model. You do that on a huge corpus, and then you have this instruction tuning here, right? And as you can see, this expansion operation is between the pre-training and the instruction tuning. So it's sort of post-pretraining. That's how they call it. They say they can efficiently and effectively improve the model's knowledge without catastrophic forgetting. They say we experiment on a corpus of code and math, yielding a new model that is initialized from LLaMA 2B, excelling in general tasks, programming, and mathematics. How do they do it? As I said, they simply take, so here is the architecture of LLaMA 2, which in highest detail possible. You have the input layer right here, which gives you token embeddings for the input. And then here you have the output layer. I'm not entirely sure, honestly. Output tokens should probably be called embeddings. Or embedding weights or something like this. Like, while we're talking about model architecture and not forward propagating signal, we should probably not call these things tokens. In any case, you get some sort of input embedding, and then you pass it just through groups or blocks of these transformer things. And these transformer blocks, usually they have some kind of attention mechanism, some kind of normalization, some kind of feed-forward layers, and so on, and then some sort of residual connection, and then there may be repeated a bunch of times or have two feed-forward connections or whatnot. But in essence, machine learning has become, in 2023, 2024, just let's repeat this thing a bunch of times and shove data into it. That's the whole, that's it. That's what our field has become. So they say, hey, given that we have all of these blocks right here, how about we kind of take them and duplicate them and only train the ones that we have duplicated. What does that mean? So you have layer. They say, let's pick some. Let's pick every third layer. So this one, and I guess that's it. And then let's duplicate them. So let's make a copy and insert it here. Make a copy, insert it here. Okay. Now you would think that that would change the output signal a lot. If you put data in here, you have some duplicated layer, some computation that's being done twice. But there is something going against that. Namely, usually you have all of these residual connections, right? These things right here. They usually take the signal and they add it to the output signal here. And that ensures many things, such as nice data flow, nice gradient flow, and so on. And you can rely on there being some sort of residual signal that's kind of carried over from the last layer. I know this isn't entirely accurate, but that's kind of carried over from the last layer. So as long as you initialize your layer such that the output is 0, right? You don't change the output of the whole network. Because, let's say this is the signal from the last layer, the signal divides into two branches. One is the identity branch that's then added with another branch that goes through your block. So these two are added together. Now, if you say the output of my block is 0, then you can see you have just the identity function that goes forward. So if you can make your new layer such that it outputs 0 initially, then you is at least immediately after copying, you get the new, you get the same network. Okay. So that we all agree on. Where it gets a bit controversial, I feel, is when they try to make it like and say, okay, now when we train, we only gonna train the newly added layers. So we're only going to train these layers that we've added, and everything else has frozen parameters, right? We just forward propagate, we back to these new layers. We'll change the new layers, which will necessarily move this away from 0. So this block now becomes active in these new tasks, and therefore will start contributing to the signal. That's also fair, right? You add parameters, you fine-tune those parameters. People do that with LoRa and whatnot. So all of that is good. Now they claim what this will do is it will kind of retain the old knowledge while adding in new knowledge. And there is where I'm become a bit skeptical, because if you train only with new data, right, you permanently change the signal. It's not like the network has an ability to detect when something is old, in the old domain, and something is in the new domain. Every single signal is routed through this layer right here. For every single signal, that block is probably not going to be 0 anymore. And therefore, for every single signal, there is going to be a changed output. Additionally, these people don't train with a mix of old and new data to kind of ensure that would be my guess, right? Let's say I do something like this. What I would do is I would mix in some old data. Maybe they actually have some. As far as I could tell, they don't. They only train with the in-domain data. And thus, the network kind of only sees that new data and it cannot adapt these old parameters, so it can't technically forget something, but it can configure its new parameters such that any of the old parameters signal is kind of distorted because there is no loss in retaining that data. And there is no signal that tells it, oh, now you need to kind of have your new layers shut up because this is clearly in the old domain. So I think this works as long as the new data has significant overlap with the old data. For example, I think there's going to be quite a bit of code already in and math in the pre-training data of LLaMA, and therefore those overlaps may be kind of enough. But I would be surprised if this was a general recipe to do more drastic domain adaptations without sprinkling in some of the old data there. In any case, that's essentially what they do. They take every nth layer, they copy it, they make sure that it initially outputs 0, so they copy and then they change the necessary weights to make it output 0, and then they train with only those weights active for training and the rest being frozen. That's essentially it. We'll go into a little bit more detail on one or two things around here. So yada, 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 blah, blah, blah. Yeah, this is what I found fun. So they say, existing works attempted to improve the multifaceted capabilities of pre-trained LLM with tailored data recipes. While feasible, they require substantial computational resources and vast amounts of data. Keep that in mind. That's kind of their criticism on the other work. Okay, we scroll down here. So we extend LLaMA 2B. Oh, we pre-train the expanded blocks on 80 billion tokens using open source code and math data for 2,830 GPU hours, 16 NVIDIA H800 for about 7 days. Do H800 exist? I thought those were H100s, honestly. If it is, I'm not aware of any GPU that's called an H800. Maybe I'm completely ignorant. But if it is an H100, using 16 for 7 days is still pretty massive. It's not as massive as full pre-training runs, but it is. But maybe all of those previous works are even more data and compute hungry. Just being said, this is not something you do at home, right? This isn't LoRa or anything like this, where it's easy peasy domain adaptation. This is still pretty huge data, pretty huge compute, just maybe not as huge. All right, and then the criticism on the other stuff is that it often has catastrophic forgetting and a decline in the model's original general abilities. So here is what they do. On the left-hand side, you can see a original LLaMA block, and on the right-hand side, a LLaMA block after identity copy. Now, this here, the left-hand side, would be one of the layers in the original network, and the right-hand side would be, so I think we made that green, right? The right-hand side would be one of the copied layers. No, I think those were blue, and those were green. Right, so you copy it over, and then you change these points here to be 0, which ensures that your output is the identity. So you can see the residual connection goes here, here, here. So if you can make sure that this here outputs 0, you're good, which means, and the best way to make it 0, because it's a feed-forward layer, you just make the weight matrix 0. And that multiplies anything by 0, and that gives you a 0 output. Then you have this thing here, again, a residual connection and a linear operation before. Again, you just put it to 0, and that ensures that the entire thing is just the residual connection at the initialization. Obviously, during training, you're going to allow all of these weights in here to be updated. It would be interesting to see what happens if you only allow the linear things here to be updated. They go a little bit into the math, and the math is rather superfluous, except for showing you, look at this operation here. There is an output weight matrix, right? So you do the whole attention thing, and you put the results of the attention in here, and then you multiply that by this output weight matrix. So that's a good point to attack by just setting that to 0. Likewise, the second component for the feed-forward network, that's some non-linearity shenanigans, but ultimately also multiplied by an output weight matrix. Again, a good point to attack and set that to 0 to make sure that everything is 0 at the output, so that is the whole thing is the identity. Now, is that a smart idea? I'm honestly not super duper sure. It's certainly smart in that probably retaining the parameters in the rest of the layer will already be kind of good in terms of there are probably some primitives in there that you can make reuse of. On the other hand, you probably don't want that stuff, copied in necessarily. You probably, if in my mind, what this could be much more, this could be more like if I had to design my block, it would probably, if I wanted to take this approach, I would probably just design a bunch of low rank adapters and then just push my computation through these layers here and back, rather than copying over the whole thing. If you fine tune, you just kind of, once they're already trained, you just kind of barely move them away. So it would be interesting to see which of these parameters actually contribute the most. Would be interesting to see, and as far as I know, they haven't done that, but would be interesting to see how much, for example, these really diverge over training and how much these two are equal. So will the zero initialized linear layer ultimately just regress to be the old linear layer with some minor modifications, because essentially the entire signal here is the same up until this point, or will it somehow find some completely different forward propagation? Yeah, the other point is, if you just zero initialize something, you kind of pay zero attention to the scaling that's kind of in the forward signal. So it is it could lead to kind of unstable stuff in here, or suboptimal stuff. Like you start out from 0 with a given signal here that's initialized at some point, then there's probably something smarter to do. There's probably a smarter way to make the output 0 or to make the whole thing the identity without just, this is like a sledgehammer you take to the weight matrix. You just be like, wow, this all goes to zero. I'm pretty, like, decently sure there should be some sort of way to achieve that in a different way. Usually what one does is one uses symmetries that exist to sort of play against each other and then always cancel out, but so that they retain a signal going forward. But that might be tricky with the residual. Like, the residual connections essentially dictate that the output here must be zero, right? I'm just wondering if that's achievable in some different way. But maybe it's entirely pointless and this works already. So in that case, yeah, I don't know. It just seems, it seems a bit weird. And then obviously what I mentioned before, right? Now you have these layers and you introduce a new one. Now, who says that if you train this, if actually what you actually want is the parameters to diverge, to learn new stuff, right? But then every signal here will be permanently altered, which I doubt that this retains the old knowledge unless there is significant overlap between old and new. In any case, I found this funny because I already told you they don't expand every single block they find. They only expand, like every fourth or something like this ultimately. So they make 4 blocks into 5 blocks by copying the last one, I guess. But here, they start out saying, given a model with blocks such and such, the block expansion incorporates an identity block after each block in the original model, ensuring that the expanded model maintains the same output. For expansion, the identity block is defined as this. And I'm like, And here down below, they go into saying, this other paper had the idea of initializing the scaling parameter in the norm modules to 0 for the construction of the identity block. However, this approach may be not effective when applied to LLaMA. They go into why that's not an effective strategy into LLaMA. I decided to look at that other paper, and lo and behold, the other paper, and you can look that up. I think it's called, well, you can see it. This is the URL right here. Stage training for transformer language models. They take a more general approach to this problem. So they just deal with, okay, how can we expand these models kind of successively while training them? It's already 1 or 2 years old already. Well, they say our depth operators doubles the number of layers, increases the number of non-embedding parameters. Given a model with layers such and such, the depth operator adds an identity layer after each layer in the original model. The identity layer is a layer where the input matches the output, namely this. So maybe they have, so essentially, how this new paper came to be, I'm going to guess, is they looked at this paper, they were like, can we do this to LLaMA? And they discovered, well, it's a bit more tricky than what they did right here. We'll have to do something else. Okay, let's just set the output weights to 0. And yeah, and then they might have this is not an accusation of plagiarism or anything like this. This is completely fine in terms of that. It's just a little bit funny that they obviously started from the same starting point and then adapted it to yourself. That's what everyone does. That's completely fine. I just find it a bit funny. And also this text right here, where they try to kind of define in numbers ultimately what they do, like their strategy for expanding layers, but their strategy is ultimately just kind of like, all right, what do you want? Well, I want to make every fourth into 5. And you're like, okay, well, every fourth we copy over. That's fine. But then they try to put some numbers on it. They're like, okay, suppose we have an initial model with L blocks. All right, check L blocks where there's already L plus 1 blocks right here, right? In their own example, from 0 to L. That needs to be expanded into L prime blocks. This constant here, L prime, we'll never see it again. Never. First, we partition the original L blocks into n groups, with each group containing L divided by n blocks. That is a fair division, right? However, how this n is chosen, who knows? Never defined, right? One would think that it has to do something with the target number of blocks, but this is just in this very rigorous definition of how many and where you should copy, that it's a minute detail that gets forgotten. For each group, we create identity copies of the top P blocks and stack them on top of each group. Okay, so there's now a number P involved as well, and one would again think that P and N in this case are probably connected to L prime, but we'll take the top P blocks and stack them on top of each group. So there's, in each group you'll have like layer, and then you take the top P blocks, let's say that's 2, and you kind of do this, right? You just kind of copy them over right here. Now, as far as I know, as far as I can tell, their P is always equal to 1. And I don't think they've done anything else. But it's good that they already, they generalize, right? That their theory generalizes and then they break it down. We arrange these blocks in an interleaved manner to maintain the structural characteristic of the transformer. Wait. What does it mean? We arrange these blocks, by these meaning the top P blocks, but how can they be interleaved when we stack them on top of the group? Like, if it's interleaved, I would expect it to look like this. I am as confused as you are right now, but in any way, all of this is completely irrelevant. I just thought it was funny. It's completely irrelevant. What you do is you go to any layer you want, you copy it, you freeze it, you freeze everything else, right? You copy a bunch of layers, you freeze everything else, and you set the initial weights to 0, and you train. That's it. Yeah, so here they go, okay, we can set these matrices to 0, and then that's it. We construct the data set of code and math. Expand the number of blocks from 32 to 40. So there's 8 groups, where each group expands from 4 blocks to 5 blocks. Thank you. Good. So here you can see the data source. This is math data and coding data. You can see there's no data of the original data set, which, so again, H8, or is this a thing? H800s? Is that a thing? I don't know. Here too. Maybe that's a thing. If it is, and it actually turns out the H800 is like very small GPU, and this is actually doable at home. I'm very sorry. I'm very sorry for my comments. Yeah, so the result I've already shown you. You can see they're good at code tasks. They're good at language tasks as well. So here are language tasks, here are code tasks, and their whole point is we can do it all and without being weak anywhere by so we've successfully taken LLaMA and expanded its domain of knowledge into these new areas. Again, crucially, I think the thing, and yeah, here the experiment, okay, if we add 1 block, add 2 block, add 4 blocks, add 8 blocks, and so on, then we get sort of better and better and better, which is fine because they add parameters, right? So naturally you would expect them to get better in training. So their whole point in their experiments is we are either as good as the old models or not much worse, or we are better in these new domains. And sometimes we're also better in the old domains. by the way. So that's the whole thing. Crucially, and as far as I can see, again, I might have missed something right here, but crucially, I don't think they've ablated kind of the weird, like the questionable things, or the things where I had questions, namely, how far away can this new data set be to not muddle up the old data set? Because if I think of catastrophic forgetting, I'm not thinking, hey, the new task should have significant overlap with the old task. I'm thinking, okay, there's something new, and I still want to retain the old stuff. And sure, if there's overlap, that's fine. But it seems to me right here that if I only train for long enough on something like this, or if this is further apart from the original training data, it's not clear to me that the model retains its original abilities. Second, I would be really interested what the specific choice of setting these things to 0 as opposed to anything else has, notably how far the parameters that are copied diverge from each other, and how far the parameters that are set to 0 converge to the original parameters, and whether there would be something smarter to do. But all in all, it is like all of the thinking, and I think and I feel, is not a substitution for a good empirical evaluation, which this lab has definitely done, and the numbers, I think, speak to that, and that this seems to be a good recipe. And if that's the case going forward, then that's all the better. The code I've seen on GitHub is said to be coming soon, so we'll see soon. That's it. Thank you very much. Bye bye.